Thank you all for coming to this experimental new type of talk. I'd like to acknowledge Mineral and Rock Physics for inviting me to give this tutorial talk. So I think we have about 25 minutes, and I want to share with you some recent types of experiments that I've gotten involved in my career, dynamic compression experiments, which has really opened up an exciting frontier of high-pressure mineral physics. All right. Oops. Sorry. Okay, so everything about in a planet, from its formation conditions to its subsequent evolution, is controlled by the properties of minerals at high pressure. As mineral physicists, we try to measure as many properties as we can along different types of knobs, such as different types of chemistry, temperature, pressure, to fill out the entire phase space where a planet might be evolving through. So from the formation conditions, whether it's a hot start or a cold start, through the pressure from the pressures of the surface of the planet all the way through the interior, how the planet loses heat and then evolves to become either a plate tectonic active state or a state that doesn't have plate tectonics, all depends on the thermal properties or the material properties of minerals in the interior. And so typically what we measure in mineral physics is crystal structure phase relations by probing the interior atomic arrangement. And this allows us to create things like equations of states, which allow us to fit and parameterize and predict and extrapolate the compression behavior of these high-pressure minerals. But what's really interesting is that now that we can conduct experiments through a wide range of pressures and strain rates, we actually have access now to what used to be the Holy Grail that was unreachable, transport properties at high pressure. And so these are the thermal and thermal conductivity, electrical conductivity, viscosity, and so the rheology of materials. And so we can move on from studying as I think Paul said yesterday, moving on from studying the thermodynamics to also studying the dynamics of materials at high pressure. And dynamic compression has really opened up that frontier for us. So if we're thinking about, from an Earth-centric point of view, but looking out to exoplanets, we might think, what if we had the same building blocks as our Earth? And so if we just compare, a typical, well, this would be atypical super Earth size, super Earth planet. Typically, we would expect super Earth class to be up to about 5 Earth masses. 10 is quite high. But if we wanted to predict what were the important phase transitions that we have to worry about when thinking about the high pressure properties, we would look at the building blocks of the oxides, silicates, metals that make up the core. And the most biggest difference is the fact that we now have to think about a huge pressure range, up to 1,000 GPa. We have to extrapolate what we know from lower pressure up to those conditions. And thanks to advancements in laser compression capabilities and shock compression capabilities, even diamond cell capabilities, we can now access these pressures and hopefully continually these kinds of pressures or temperatures as well. And so what we do is we actually have to now make a description of materials, of matter, over an entire range of pressures, temperatures, and timescales. And so what we're looking for is a sort of a universal description over pressure and temperature regimes that have completely different physics. And so moving from describing the atmosphere of a planet, using the ideal gas law, PV equals nRT, all the way to super high pressures that would be found in the interiors of planets, where the electron overlap is so high that that they would behave in a very different manner. And so what dominates the interactions of atoms and electrons at different conditions is vastly different at different pressures. And so this has been really exciting being, a high-pressure mineral physicist, because we start to enter into the regimes where we have to worry about the electron-electron scattering. We have to worry about the core electrons, not just the valence electrons interacting with each other. And so it's a quite exciting time to be in this field. So if I impress anything on you today, it's that this is a really exciting frontier of physics, but also of geosciences as well, because of the application of what we're measuring. But I'll talk a bit about some of the new techniques that enable us to get to these high pressures, and they all come with a lot of different pros and cons to them as well. But I won't be able to go into very much detail, but I want to give you a bit of a flavor of some of the new techniques that are out there, and that'll completely change the way that we do science, because every single year new user facilities are coming online, where the rep rates are going much faster than we can actually keep up with now. And so the high pressure frontier is expanding rapidly. And so one other thing I wanted to also point out was that all the caveats I point out, the downsides of what we're measuring, turn out to also be opportunities to learn more about the materials that we're studying as well. And so if something is rate limited and so we're affected by kinetics when looking at a phase transition, it also tells us about the activation energy and the mobility of atoms at those conditions and those timescales. So as I mentioned this before, what's really cool is that we're riding the technology development of lasers and of X-ray lasers. I remember being a graduate student when the first X-ray laser had light, and you could spray a protein through an X-ray beam and get a diffraction pattern. And all of my friends that were spending their summer crystallizing proteins to get something big enough started to wonder what they were doing with their time. But what's crazy is that instead of putting people out of certain types of jobs, what it does is it expands the accessible types of science. And so what's amazing is that we can now study on the timescales of atomic mobility snapshots of how the atoms are arranged because of things like the X-ray lasers and these big laser systems. I'll get to that in a second. But what I wanted to also encourage everyone to read was a recent open source or open access summary article by Tom Duffy and Ray Smith, my postdoc mentors, on this subject as well. I never expected, or I never imagined that I would be working in a field where it seems like the science that we're being told about sounds a little bit like science fiction. What's crazy is that we apparently, we used to think that matter got simpler with pressure. As you squeeze metals, they become simple, close-packed, and become more close-packed. But what has been found in the past 10 years or so, or lately, is that as you go to higher and higher compression, the symmetry actually doesn't become just close-packed and simple, but we actually have really complex structures. And this is because, as I mentioned before, we have participation of the core electrons in addition to just the valence electrons. And so there isn't enough space for our typical bonding rules to control. And so we find things like host-guest structures where there are two interpenetrating lattices. We find electrides, which is when you have a valence pair come together and then pop into an interstitial site, and it causes, for example, sodium to become transparent because you have a electron pair acting as what an atom would otherwise. And you have superionic ice, where you have a lattice of oxygen atoms with delocalized hydrogens bouncing around, and that's a different charge carrier completely. And so the more that we look at matter at extreme conditions, the cooler phenomenon that we find, and it really makes us, it speaks for a need of exploring more, because all of the ways that we interpret how bonding works at low pressure are now going to be completely out the window at higher and higher pressures. And so it really is a different periodic table. This is a little bit less crazy, but this is what I study, is looking at different analogs and seeing if we can learn more about what controls phase transitions by tuning things like chemistry, which allows you to tune basically the electronegativity or other bonding behavior. And so a cool aspect of doing dynamic compression is that we can actually look more into these phase transitions. And so sodium chloride, for example, when you compress a diamond cell, we know the equation, the phase diagram very, very well. But in dynamic compression, if you compress along the 1-1-1 direction, you transform at the same pressure as you do for diamond cell. But if you transform along the sides of the cube on the 1-0-0, you have to overdrive by a couple of GPa. And so this tells us that the energy pathway is more accessible when we compress along the 1-1-1 direction. And that's really cool. These mismatches tell us more about the nature of matter. And so it's really interesting that we think of these different analogs as different ionic, or we can categorize them in terms of either cation size. This is, in the upper right corner, I show a plot of transition pressure from B1 to B2. I apologize for the small font. It's made in Excel. But what it shows is that, thinking about transitions in terms of, Pauling's rules, what is the cation to anion ratio? Does that control the transition pressure? Or is it something more interesting? If we look at the phase diagram of lithium fluoride, another, ionic, simple, B1 structure, we see that it never actually, at room temperature, transformed to the B2. And so the phase diagram looks very different. And so we can start to ask questions about, at high pressure, or what is the utility of an analog, and how does that teach us more about the nature of atoms and how they interact? What's really cool is that the experiments that we do at these super extreme conditions are important for not just geosciences and planetary sciences, but also nuclear fusion energy development and weapons development. And so there's a lot of people also interested in extreme physics. And what's interesting is that they define high energy density physics as over 100 GPa. 100 GPa isn't so high of a pressure. And so it's funny to hear and work in an interdisciplinary field where the same sorts of terms get thrown around and sound inaccessible, but then they're just 100 GPa, not so bad. We had those in our own Earth. But I wanted to show this because I thought it was funny that there's this summary book that is available online called High Energy Density Physics, or Frontiers in that, the X Games of Contemporary Science. And so it's a fun field. Again, I keep talking about these developments with the ability to tune the compression rate and the pressures and temperatures that we get to, which is starting to become more and more accessible with things like ramp compression or designer targets where you can tune the porosity or tune the load rate. We can then really aim anywhere we want to go in the pressure, temperature, volume, space, and start to ask questions of, what are the interesting questions that we want to aim for in the future? And so I want you to think about that as we, go through the talk. So there are a few different ways to get to high pressure. I'll be focusing on dynamic compression on lasers in the end, but it's just one method. Diamond anvil cells are able to reach extremely high pressures now with developments in the double-stage diamond cell toroidal DACs. And so the double stage, I believe, was able to reach over 1,200 GPa and get a diffraction pattern at room temperature. The highest, so gas guns can get you to a couple hundred GPa. And again, there's developments in pushing all of these techniques to higher and higher pressures. Pulse power is a type of technique where this is at the Z machine in New Mexico. With electricity, you slam plates into each other. And so it's another way of also, you can have great control over the rate and the change in rate of those plates. Today I'll be talking about laser compression. Laser compression is achievable when you focus the laser onto the back of your sample. And it creates a plasma. And so, a target surface that is low in Z, low in atomic number, is easier to create a plasma. You don't have as many electrons to pull off. And so as you create that plasma, the plasma expands backwards and sends an equal and opposite force into the sample. And this is how we compress materials. And so if you do this, with a lot of power up right at once, and so we can send a shock wave through the sample, but you can control the laser pulse shape that goes into it, and then bleed in the energy slowly and not actually ever reach shock compression. And so a lot of the ways that we try to design experiments is all dependent on when do materials shock up. As materials go to higher pressure, their inherent sound speeds are faster as well. And so every wavelet traveling behind the front wave is moving at a faster speed. And so they coalesce. It's very easy to coalesce and become a shock wave. And so ramp compression, you try to take advantage of the fact that some materials are strong and you won't have as much of a coalescence. And so there's different ways to play around with the loading shape. And it's really a cool, but also frustrating technique too, because it turns out that plasma dynamics is really turbulent, and there's a lot of scaling laws, and not much is known about how the plasma expands and then is able to hold and sustain its shape. And so we're limited to things like 5 to 10 nanosecond drives, but also trying to push things to longer time scales as well. Also, lasers are really energy costly as well. When we think dynamic compression, the first thing that comes to mind, of course, is shock compression. Shock compression can be defined as the material response to impacts and explosions. And so, again, we send pressure waves through the sample, and the rise time of a shock wave is dependent on the material properties, and that's on the order of picoseconds. But the pressure density path that it follows is set by the fact that that they follow a higher temperature path. And so one difficulty with dynamic compression for a long time was the fact that only shock compression was achievable. And so all of the interesting materials that are of interest to our planetary interiors, for example, all melt too low of pressure to be relevant to super Earths and exoplanets. But now, if we ramp compress, again, as I mentioned about how we can tune the ramp rate, we can access different cooler temperature states. And so we can go to higher pressures and measure conditions that are more similar to those of adiabats inside of a terrestrial planet, for example. But we can also explore the higher temperature side of the Hugonio as well if we use a porous sample, for example. And so there's different ways to, again, tune where we can go into high pressure. Some examples of recent work that I've done is looking at the equation of state of iron at super high pressures. And so if we compare the compression of ramped iron and ramped iron silicon alloys, compare them to extrapolations from lower pressures from diamond cell, it's actually quite surprising that the room temperature descriptions of measured actually hold up quite well when you extrapolate to higher pressures. And that mostly speaks to the fact that although we're following what's closer to an isentrope rather than room temperature, the knob of pressure is so great that dominates the volume. And so thermal expansivity is much smaller, much less important at those high temperatures. And so we were able to study, what would be, for example, the effect on the core of a terrestrial exoplanet, for example, with these kinds of experiments. But what's really cool is that there are lasers all over the world, and there are X-ray sources all over the world, and mixing and matching them is becoming more and more increasingly possible, and it's so exciting. Every year there's a different facility coming online, and so really, the strengths of being able to explore strain rate as a knob in terms of how we pose experiments is really exciting. So a little bit about the diagnostics. One of the ways that we track pressure is by looking at using velocimetry. So looking at the speed of either the shock wave or the particle wave, or and so looking at that as a function of time, and then extrapolating that back into what the material properties are at the sample conditions themselves. And so we can do this a few different ways using either point or one-dimensional or two-dimensional velocimetry. And so point visor is one dimension, and we can do line visors. And so basically, the optics in the experiment limit what we have access to, but having two-dimensional information of the shock front as it propagates through your sample is something that is only in development now at the national labs. And it's so exciting to see how it's more than just a simple, we reach this pressure. It's what's the structure of the sample? What's the lateral heterogeneity? Does that tell us about the rheology of the sample? It's pretty cool. And then photon Doppler velocimetry, PDV, is another type of interferometry technique. And so they have all of their pluses and minuses in terms of the pressure range that they're useful for, or the specific questions themselves. And so and also just most accessible because these are all these techniques are in development, but they're available at different beamlines and increasingly more and more so. Another technique is looking at the emitted photons, and so this is using pyrometry. And so the better coverage that we have of the entire wavelength spectrum, the better we have a constraint on temperature. But at different places, we use what we can, where we look at just the emitted counts of photons, and then use that and compare it to a calibrant to determine what the temperature is emitted from our sample. And we can take advantage of this in experiments of decaying shock, where we send in an unsupported shock through a sample. And as an unsupported shock travels through the sample and emitting out of the front of the shock, a skin depth from the shock front is actually just the black body, gray body emission. And so we've been successfully using that to measure temperature. And this is a really nice study by Marius Mio looking at different analogs of quartz and how the temperature measurements of those three can actually give us constraints on the melting curve of SiO2 across a wide range of temperatures. And so the amount of jog that occurs when at that transition is directly related to the enthalpy of the enthalpy difference of the two phases. Another type of diagnostic is X-ray diffraction, and this is available in 1 nanosecond chunks at the omega laser, for example. And so this is using a foil in which this is called a backlighter setup, where a very, very, very powerful laser turns a metal foil into a plasma. And so if we create mostly helium-like states, the emission will be helium alpha dominated. And so this is how we create a monochromatic X-ray source at very large laser facilities. But we can also pair dynamic compression experiments with synchrotrons and with X-ray lasers. And so this example that I show here is an X-ray diffraction pattern collected at the dynamic compression sector in at Argonne National Lab, where Sally Tracy measured the formation of stishovite using different starting materials of SiO2. Other work that people do is developing the spectroscopy techniques at different beamlines. And so this is made possible either by using an imploding sphere to emit a broadband, or by using synchrotrons as well. And so looking at the ordering of atoms, not just by using not just looking at a snapshot of the atoms, but also looking at the small range order as well is made possible by these. And so this is another way to potentially back out temperature as well. And people have successfully done Raman spectroscopy at the same time as doing dynamic compression as well. We look at the reflectivity of the shock front, and that can be correlated to, for example, the metallicity or the emissivity of a material. And so combining the emitted or the reflectivity properties with things in situ probes like X-ray diffraction allows us to really leverage all those different techniques together. One example of a study that we're going to submit very, very soon is how we were able to use X-ray diffraction, in situ X-ray diffraction, during shock compression on the MGO Hugonio, to show that these large excursions in the pressure temperature Hugonio that have been measured are correlated with solid-solid transitions of the B1, B2 structural transition. And so having both the in situ X-rays and in situ temperature measurement allow us to correlate these different changes to each other. What was really surprising also is that if we look at this material and look at it and shock along a different orientation, we get a different answer in temperature. And so we have sensitivity to orientation dependent effects. And so this is potentially a way for us to be able to really explore the atomic motion and the non-hydrostatic environment, as the shock wave is propagating. And so looking at how we can access potentially different transitions, structural transitions, by looking at both the temperature and the X-ray diffraction measurements allow us to potentially answer this question. But as we're finding with experiments in this regime, a lot of what we expected to find in terms of transition pressures were not so. And so it's really fun to be able to have experiments that are evolving or coming up with answers as as theory is also coming up with different answers as well. And so trying to figure out what's the physics that we're missing when trying to interpret the data that we get is the most fun part of the job that we have. And so I wanted to end just on one more example. When we look at the equation of state of the material or phase diagram, we're looking at the thermodynamics. But the Holy Grail, as I mentioned, in terms of the evolution of a planet, is to look at the transport properties. And so some of the experiments that are accessible, that are possible because of the fact that we're compressing our materials very uniaxially but very quickly, allow us to take advantage of the fact that it's a dynamic experiment. And so when we laser compress our materials, we have a lot of flexibility, as I mentioned, but we're looking always for smoother and smoother drives. And so instead of just directly blasting your lasers at material, you can blast them on the inside of a hull ROM, which is a gold tin can, basically. That turns into a super hot material, emits X-rays. Those X-rays hit your sample, and that could be a way to drive your sample to high pressures. Or you could even do it one step further, where your tin can irradiates a brominated plastic layer. That turns into a plasma, propagates across a vacuum gap, hits your sample very slowly like snow. This is like a Rube Goldberg type of device. So different ways that we try to smoothly bring pressure up. So it turns out this was a technique people tried to develop to try to create longer drives and more stable drives, but they realized that the heat wave, because this hot plasma was touching, then also catches up through the sample. And so one experiment's loss is another's gain, and so now we have a way-dimensional thermal conductivity if we do our experiment right. And so a project that one of my graduate students is attempting to do is to use these types of experiments to try to constrain the thermal conductivity of iron at the planetary interior conditions. But we don't know if it's going to work or not, so stay tuned for that. So in conclusion, we have an amazing opportunity as a field to access a frontier of states that are relevant to not just what we thought would be relevant to exoplanets, but also what we didn't think would be relevant, and things that are more and more relevant to exoplanets. But anyway, these experiments are made possible because of developments funded by the government and operated by national lab scientists and operated by user facilities. And so having an entire team of laser scientists behind us when we come and do experiments is such a treat. And so I hope that you all join me and start using these facilities, because they're really exciting, and the frontier is out there for the taking. All right, well, I'll take any questions. Thank you for your time.